Here is a combined summary of the 4 pages. Graphs are fundamental data structures used to represent relationships in various domains, often exhibiting global sparsity with pockets of high edge density. A fundamental task in graph mining is to discover these dense subgraphs, which has a rich set of applications in fields such as social sciences, bioinformatics, cybersecurity, and more. This paper introduces a new definition of regularly triangularic (RTR) families, which capture the notion of dense subgraphs that contain many triangles and have degrees comparable to the subgraph size. The authors design a provable algorithm, RTR extractor, that can discover RTR families that approximately cover any RTR set. RTR extractor is efficient and inspired by recent results that use triangle counts for community testing and clustering. The algorithm's primary utility is shown by its guarantees on the output, ensuring that every omega-1 regularly triangularic set has a constant fraction of its vertices in the output. The authors also discuss the importance of triangle density and how it implies edge density, making the algorithm efficient for finding dense subgraphs. Experimental results demonstrate that RTR extractor has excellent behavior on a large variety of real-world datasets, covering a quarter of the vertices with subgraphs of edge density more than 0.5, for datasets with 10m plus edges. The authors provide a theoretical framework for dense subgraph discovery, using triangle density as a guide. They define the notion of RTR sets and prove strong theoretical guarantees on algorithms. The empirical goal is not recovering RTR sets but discovering practical dense subgraph discovery algorithms. The paper demonstrates the utility of RTR extractor for unsupervised graph discovery tasks, correlating the output with meaningful sets of similar vertices in a citation network. The paper introduces the RTR extractor algorithm, a novel approach for identifying dense subgraph families within a graph by leveraging triangularic sets. This algorithm iterates through an extraction process that removes edges and vertices, ultimately leading to the formation of regularly triangularic sets. The key insight behind this approach is that the neighborhood of a vertex in the cleaned graph is automatically rich in triangles, allowing for a simple BFS-BASED algorithm to extract dense and triangularic sets. The analysis of the RTR extractor begins with 2 parts. First, it shows that the output of RTR extractor is omega-1, regularly triangularic. This is achieved by proving that the cleaning operation in step 5 removes edges that reduce triangle density, and that the degrees in the output set S are within constant factors of each other. Additionally, the paper demonstrates that a constant fraction of any omega-1 regularly triangularic set S is contained in the output of RTR extractor. In the well-separated case, the analysis becomes more complex as it requires arguing that there is a single extraction step that removes a constant fraction of S. This involves a careful examination of how vertices in S get deleted from the current subgraph H. The parameter beta plays an essential role in preventing many vertices of S from ending up in other extractions. The main argument revolves around the idea that only an extraction seated inside S can remove a significant part of S. The paper concludes by encapsulating the analysis as a lemma, which directly implies theorem 3.5. This theorem states that a polynomial fraction of vertices of S is present in the family T, with all constants being polynomially related to each other. The proof of theorem 3.5 is also detailed, considering 3 possible cases for the seed vertex V of an output set T. V is in S, the neighborhood N, V, intersects S, or a vertex from S is added to T in step 13. Each case is addressed separately, utilizing the well-separated condition and the choice of epsilon and beta as alpha squared and alpha squared divided by 4, respectively. The paper discusses a novel algorithm called RTR extractor, which aims to cover a graph with dense subgraph families. It starts by covering a graph with dense subgraph families, focusing on triangularic sets. The algorithm's running time is analyzed, showing an upper bound of O, T plus, M plus N, ln, where T is the running time of triangle enumeration. The paper also presents experimental results on various datasets, comparing RTR extractor with state-of-the-art procedures like K-core decomposition, 2, 3, nucleus decomposition, Louvain algorithm, iterated Charaker's greedy peeling algorithm, and flowless. The results show that RTR extractor significantly outperforms other methods in terms of coverage at high densities, especially in networks with high clustering coefficients. However, it lags behind in datasets with lower clustering coefficients, such as the DBLP citation network. The paper concludes that RTR extractor is a highly effective method for finding dense subgraphs in networks, especially in social networks and collaboration graphs. The research paper presents a novel method for discovering dense subgraphs in networks, introducing the RTR extractor algorithm. This algorithm effectively covers a significant portion of vertices in dense subgraphs, outperforming other methods like Louvain and greedy. The strength of RTR extractor lies in its ability to extract dense subgraphs with high edge density, often missed by other methods. The algorithm's performance is demonstrated through various datasets, including social networks, citation networks, and email networks. A case study on a computer science citation network showcases the algorithm's ability to uncover clusters focused on specific topics without prior knowledge of the network's semantics. The results are visually supported by figures and tables, providing a comprehensive understanding of the algorithm's performance and the significance of its findings. The paper also discusses the RTR extractor algorithm's efficiency and accuracy in identifying dense subgraphs, especially in cases where the subgraph is sparse or has a high variation in induced degree among vertices. Here is a combined summary of pages 13-14. The concept of covering a graph with dense subgraph families via triangularic sets is explored, building upon existing work in dense neighborhood graph discovery. Specifically, the approach of Huang et al. 2010 is referenced, which introduced triangulation-based methods for identifying dense subgraphs. Moreover, the work of Yichen Xu et al. 2023 is cited, which presented efficient algorithms for generalized densest subgraph discovery. The importance of dense subgraph discovery lies in its applications to network analysis, such as weighted gene co-expression network analysis, as demonstrated by Bin Zhang and Steve Horvath, 2005. The key idea is to identify dense regions in the graph, which can reveal meaningful patterns and structures. To achieve this, the authors propose a novel framework that leverages triangularic sets to cover the graph with dense subgraph families. Triangularic sets are essential in this context, as they provide a compact representation of the graph's dense regions. By efficiently identifying and combining these sets, the framework can effectively cover the graph with dense subgraph families. The mathematical formulation of this approach involves representing the graph as a set of triangles, which are then used to construct a triangularic set. This set is subsequently utilized to identify dense subgraphs, ensuring that the resulting subgraph family provides an effective cover of the original graph. The author's framework offers a promising solution for graph analysis, enabling the discovery of dense subgraphs and their applications in various domains.